Hello, this is section 4.6, rational functions and models. So the rational function means when the function comes with the numerator and denominator, and then both of the numerator and denominator must be a polynomial, and then we can call the rational function. So domain of the rational function includes all the real number except the zero of the denominator. And graph of the rational function is continuous except the x value where the q of x equal to 0. So number one, determine if the function is rational and state it's a domain. So if it's a rational, we're going to talk about domain. If not, we don't have to worry about it. All right, so first, the example. All right, so first of all, is it numerator polynomial? Yes, it's a linear. Is it denominator polynomial? Yes, it's a quadratic. So yes. So these two are the polynomial. That means this is rational. So yes, it is rational. Then now we can talk about domain. So domain means the q of x equal to 0. So q of x shouldn't be a 0. So q of x is a denominator. So 1 minus x squared equal to not equal to 0. So 1 minus x times. Oh, let's use the square root property, okay? You can do that too, but yeah. So if you multiply, add x squared both sides, you got 1 equal to x squared, and then square root both sides, plus minus, x equal to plus minus 1, right? So this is can be the x, okay? So all real number, except the x shouldn't be a plus minus 1. Okay. Alrighty, so and then for the second one, this one, denominator is a quadratic, so yes it is, but the numerator, which is this, is not a polynomial. This is not polynomial. Actually, this is a cube root, which is a radical, so it's not rational. So we don't have to worry about the denominator, okay? All right, let's look at the next page. Suppose that a construction zero can allow the 50 cars per hour to pass through the cars arrived randomly at a rate of the x car per hour. Then the average number of the cars waiting in the line to get through the construction zone can be estimated by n of x equal to x squared over 2500 minus 5x. So we want to evaluate each value. So first one is n of 2ne, which is you got to put 20 square over 2500 minus 50 times 20, and then it's about 4 over 15, and then I got approximately 0.27. If I plug it in 40, which is 40 square, and 2500 minus 50 times 40, approximately 16 over 5, and about 3.2. And the n of 49, which is 49 square, 2500 minus 50 times of 49, I got 2401 over 50, and then it's about 48.02. So now in B, explain what happened to the length of the line as x approached to 50. So as you notice, when x approached 20, 40, and 49, and then number is actually getting bigger and bigger, right? So which means as x approaches to the 50, and then the line dramatically. It looks like almost exponentially, right? Okay, and then we can talk about vertical asymptote. So vertical asymptote means it's a vertical line, which is the x equal to k. So k, you can change that, and then so when x approaches the infinity or the x approaches the negative infinity, f of x that, and then when x is when approach the k from the either left or the right. Okay, so yeah, so when you actually the graph, and then this is actually the express the vertical asymptotes. All right. Also, the horizontal asymptotes, the line y equal to horizontal asymptote of the graph so of the f. So if f of x approaches to b, as the x approaches to either infinity or negative infinity. So we are looking for the y value instead of the x value. Okay. So the finding of vertical horizontal asymptote. So which is the asymptote is vertical horizontal asymptote is like this one. Okay. So graph never kind of not touching the asymptotes in here. So when you have a vertical asymptote, so to find the vertical asymptote, set the denominator equal to 0, and then you can solve for it. And k is a 0 of the q of x, and then x equal to k is a vertical asymptote. But caution, if the k is a 0 of the both q of x and p of x, f of x not written as the lowest term, so because the x minus k is a common factor, which is we have to cancel this out. Actually, so instead of you getting a vertical asymptote, we might gonna have a hole. And the horizontal asymptote, if the degree of the numerator is less than the degree of the denominator, is always gonna be the y equal to 0. And if the degree of numerator equal to the degree of the denominator, y equal to a over b, which is these are the leading coefficient. Horizontal asymptote, where is the leading coefficient of the numerator, and b is the leading coefficient of the denominator. And then c, degree of the numerator is greater than the degree of the denominator, and then there's no horizontal asymptotes. Okay, so they compared to then three things. All right, also we have a slack and obligate, slack or obligate asymptote, which means this is a forms of y equal to mx plus b. Okay, so third type of the asymptote, which is neither vertical nor horizontal, occurs when the degree of the numerator of the rational function has a degree 1 more than the degree of denominator. And then, so see here, this is degree of 2, but this is degree of 1. So in that case, this is actually give you the slant asymptotes. Okay, so slant asymptote means this one. This is slant asymptotes. Okay, and so use the graph to determine the any vertical and horizontal asymptotes. So as a vertical asymptote, which is these are the vertical asymptotes. Okay, which means this is x equal to 2 and x equal to negative 2. And then also the horizontal asymptote, which is this is a horizontal asymptotes, which is I can see that is y equal to actually about negative 1. Okay, so vertical asymptote and then the horizontal asymptotes. On this case, I don't see as a vertical asymptote, right? I don't see any of the can be that because this is continuous. But horizontal asymptote, I think when x goes to infinity and the x goes to negative infinity, and then f of x actually goes all the way to here, right? They try not to touch the x-axis, okay? So I want to say horizontal asymptote is y equal to 0 for this case. All right, next page. Now, we want to determine any horizontal vertical asymptote for each rational function. So in order to find the vertical asymptote, you just set the denominator equal to 0. So 1 minus 2x equal to 0, and so for x. So 2x equal to 1, x equal to 1/2. And then the horizontal asymptote, we have to check the degree. So degree of numerator is 1, degree of denominator is also 1, 2. So it's the same degree. And then your horizontal asymptote will be y equal to, and then from the leading coefficient. So it'll be leading coefficient on the top is 3 over negative 2. So negative 3 over 2. For the b, okay, vertical asymptote, which is denominator equal to 0, which is x squared minus 3x plus 2 equal to 0. And this is x minus 1 times x minus 2, x equal to 1, and x equal to 2. So there are two vertical asymptotes. And the horizontal asymptote, you got to check the degree. So degree of numerator is a 1, and degree of denominator is 2, which is a numerator degree is less than denominator. So we have to say y equal to 0. And then h of x, vertical asymptote. So it's the degree of the vertical asymptote, which is this one actually. We gotta work it out, okay? So x plus 2 times it's a factorable. And then what happened is you can cancel the x minus 2 over x minus 2. It becomes x plus 2. So you got the reduced expressions. In the case, okay, so this time actually there's no vertical asymptote, but there is the hole this time. So hole will be when x equal to 2, which is you just cancel, and then when you plug it in 2 into the x plus 2, which is 2 plus 2, which is a 4. So there's a hole in the 2 and 4. So you get the hole this time. All right, but there's no border. And then also there is no horizontal asymptote either, because the degrees are 2 and degrees are 1, right? Yeah, so there's no horizontal asymptote. So horizontal asymptote, sorry. Horizontal asymptote, which is none. All right, next problem. So now graphs and transformation of the rational functions. Graph and rational functions are very greatly in complexity. We begin by graphing y equal to 1 over x, and then the use of transformation to graph the other rational functions. So if you graph the y equal to if you graph the y equal to 1 over x, which means this is actually the graph of, there is a vertical asymptote, there is actually the vertical asymptote, which is x equal to 0, okay? So it can go through the y-axis, and then for the horizontal asymptote, which the degree of the numerator is 0, denominator is 1, so y equal to 0 is also the horizontal asymptote too. And then when you plug it in 1, it'll be 1, plug in -1, become -1, right? So this is actually the graph of y over x, okay? But in here, in the example 5, this one says 1 over x minus 2. So this is actually the horizontal transformations, which means you have to go right to units. So right to unit means any of the things should be moved, okay? So which means I'm going to use a red, and then this must be moved 1, 2 right here. And this must be 1, 2 right here. And also, the vertical asymptote also need to move to the 2 units. So it's going to be right here. And then horizontal asymptote is going to move to the right, still stay the same. And then your graph becomes here. Your graph's going to be right here. Okay? And then for the example 6, this is actually the left to the 2 units and then down to 1 unit from y equal to 1 over x, okay? So if I use the blue for the parent function, which is a basic function, okay? And then if I grab this one, I have to move, use a red, okay? I have to move it to place the left and then down 1, so right here. And then to place the left, down 1. And also the vertical asymptote need to move to the 2 units too. So from this one, so 1, 2. So your asymptote, vertical asymptote right here. And then for the horizontal asymptote, need to go to the down to 1. So it's gonna be right here. And then your graph will be this. All this. Okay. All right. Let's look at the next one. Example 7. So use the graph 1 over x to sketch the graph of g of x, and then write the g of x in terms of the f of x. Okay, so which means so we're gonna say g of x is actually for the f of x in terms of f of x, right? So we gotta do f of, we go to the left and then down 1. So yeah, that's what it is. So we go left 1 and down 1, right? From the basic functions, which is 1, 1, -1, -1, right? So this time we go down 1 and then left 1, down 1, left 1, which is a down 1, and then left 1. And then your graph is going to be this. Alright, so that's it. That's what we call the transformation. So graphing a rational function at f of x equal to p of x over qx defines a rational function in lowest term to sketch the graph followed the step. So when you do that, find the vertical asymptote, horizontal asymptote, or oblique asymptote, and then y-intercept, x-intercept, and determine the whether graph will be intersect in non-vertical asymptote y equal to b, solving as f of x equal to b, and where the b is the y value of the horizontal asymptote. By solving f of x, mx plus b, where the y equal to mx plus is equal to the oblique asymptote, and then plus some more points and the x value in the each interval of the domain determined by the vertical asymptote and x-intercept, and then complete the sketch. Alrighty, next problem. So the next problem, yeah, we gotta do the few steps, right? So first thing is, okay, so step 1, okay, I need to find the vertical asymptote, which is x plus 3. Oh, no, sorry. 2x minus 4 equal to 0. So x equal to 2. So that's a vertical asymptote, which is x equal to 2. And then we got horizontal asymptote, which is check the degree 1, 1, which is y equal to 1/2, which is 1/2. About here. Okay. And then we have to get to the y-intercept, which is plug it in 0 as x, so 0 plus 3 over 2 times 0 minus 4, negative 3 over 4, which is 0 and negative 3 over 4, so which is about here, still greater than negative 1. And then x-intercept, which means the numerator equal to 0. So x equal to negative 3, which is negative 3 and 0. So negative 3 and 0. So here, 1, 2, 3, negative right here. So I think we can graph for this regions, which is goes this way. Yep. And also we have to find out the graph is gonna be here or here. So what I needed it, I'm gonna use 1, 2, 3, 1, 2, 3. I wanna use the x equal to 3. So if I plug it in, f of 3, let's see what happens. So 3 plus 3 over 2 times 3 minus 4, 6 over 2, which is 3. So it's a 3, 3. So 3, 1, 2, 3 here. So yep, this is a graph. Okay. Now g functions. The first one, vertical asymptote. Okay, so vertical asymptote, we got the, oh yeah, this one actually we need to factor out some cancellation, okay? So 3x minus 1, x plus 2 over 2x minus 1 and x plus 2, which is x plus 2 cancel. And then we got 3x minus 1 over 2x plus 1. So vertical asymptote is we have to find from here, okay? After the videos, okay? So 3x sorry, what am I keep saying it? Sorry. I have to say 2x minus 1, which is equal to 0. So x equal to 1/2. So 1/2 is right here. Okay, and then horizontal asymptote, which is same degree, numerator denominator, so y equal to 3 over 2, which is 1/2. And then y-intercept, plug it in 0, which is f of 0 is going to be negative 1 over 1 is 1, so 0, 1. So y-intercept is 0, 1. Y-intercept, yeah, y-intercept is 0, 1. Okay, and then the x-intercept, which is numerator equal to 0, so 3x minus 1 equal to 0, so x equal to 1 over 3. So 1/3 and 0. So 1/3 0 is about here, is 1/2. Okay. And then you get the graph of this one to actually, okay, but we have to kind of check it out though. Okay, so in here, what we need to check that is, okay, there is a hole this time. Because of that, we're getting a hole. Which means when x equal to -2, because -2 makes it 0, right? And then when you plug it in to this function into in this function, okay, so which is x is actually x is -2, so you got 3 times -2 minus 1 and 2 times -2 minus 1. It becomes it becomes the 7 over 2, 7 over 5. Okay, so which means when x equal to -2, which is we getting a hole here, so -2, which is about this place. Oh, sorry. So about here. So when -2, yeah, this is a hole. So this is connecting it this way. And then in order to find which of the region is a graph, where's the graph of the which region, I have to actually use the f of, let's say, f of 2. 1, 2, 2 is fine, 1 is fine. So if you plug it in 1, 3 times 1 minus 1, and 2 times 1 minus 1 is 2 over 1, which is 2. So 1 and 2 are here. So your graph is right up here. Okay. All right. So that's what it is. Alrighty. So that's all. Thank you for listening.